Okay, so let me start. Okay, so last time we recalled the definition of smooth manifold, and we talked about the definitions of smooth functions on a manifold. So this is your manifold, and you have a function then it's smooth if whenever I take a point on the manifold, if I take a chart near it, phi, then the composition F composed phi inverse. That's a map from an open subset of some Rn to R. This map should be smooth. Okay, this function should be smooth. And similarly, if I had a continuous map, let me just call it F again. Okay, so between two smooth manifolds, then this was smooth if whenever I take a point P here, I look at its image Q, then by continuity, if I take a chart around Q, I can choose a small neighborhood of P where I have a chart which maps into this neighborhood of Q under F. And so then I can look at the two charts here, say phi and psi, and then I get a map between open subsets of Euclidean spaces, psi composed F composed phi inverse. This should be smooth. This is between open subsets of some Rn and some Rm. All right. So we've defined smooth maps between manifolds and smooth functions on manifolds. The next step is to define what is the tangent space to a manifold. So this is actually a bit non-trivial for the following reason. I mean, if your manifold is embedded inside some Rn, so for example, the sphere, say S2 in R3, then it's easy to define the tangent space. So in this case, it would be the tangent plane at a point on the sphere, to the sphere. And so in this case, the tangent space is identified with a subspace of Rn, with a vector subspace of the ambient space. The problem is to define it intrinsically. So, I mean, this is important because I mean, why do we want an intrinsic definition? because many manifolds naturally occur as quotients without embeddings into Euclidean space. Okay, so I mean, in this case for the sphere, so if M is embedded into some Rn, then we're okay. Then TPM, the tangent space, is a subspace of Rn in a natural way. This is a subspace. But in general manifolds, for example, the standard torus, let's say, you can get it by quotienting sides of a square, right? Opposite sides of a square. So this gives you an abstract manifold as a quotient of some subset of Euclidean space, right? This square modulo quotient relation. So it doesn't come with any preferred embedding into Euclidean space, right? So in this case, how would one define the tangent space? So we want an intrinsic definition. Okay. So, I mean, manifolds as quotient spaces, I mean, for Utsav and Rudroda, you also, I mean, the most common example for you is, say, G mod K. So this is an abstract manifold, right? So how does one define tangent spaces in this case? Okay, so there are different ways to define the tangent space. So one way is a geometric way. So I won't go into details about this geometric definition. The idea is you look at curves. So you have a point P in your manifold, and you look at curves passing through P. So smooth curves. Okay. So here gamma from an interval AB into your manifold is smooth, means that if I compose with a chart, then the curve that I get in Rn, this curve phi composed gamma in Rn is smooth. Okay. And one way to define the tangent space is to think of tangent vectors at P as velocities of curves, smooth curves passing through P. Now, how do I define the velocity of a curve? I can't, right? Because I mean, my curve is taking values in M. So it doesn't make sense to differentiate it. Instead, abstractly, what one does is you look at the set of all curves, gamma, smooth curves, which pass through P at time 0. And then you quotient this by an equivalence relation where gamma 1 is equivalent to gamma 2 if, when I look in a chart, phi, then phi composed gamma 1 and phi composed gamma 2, these are two curves in Rn. These should have the same derivative at time 0. Okay, these should have the same tangent vector at P. Okay, so I mean at phi of P. So okay, so if for a chart phi near P, okay, and it's easy to see if this holds for one chart, then this will hold for any other chart near P, because if I take another chart, I mean, the two curves in Rn will differ by the change of charts map, which is a diffeomorphism, which will take tangent vectors to tangent vectors. So if two curves have the same tangent vector under one chart, then they'll have the same tangent vector under any other chart. Okay, so you can define the tangent space in this geometric way. Okay, so this would be a geometric, a very intuitively natural definition of the tangent space in terms of velocities of curves, right? So you take all curves passing through P and you quotient by this equivalence relation. So any questions about this? Any questions? So, I mean, what's the problem with this? We want the tangent space to be a vector space, right? In this case, it's not clear how to define the addition on the tangent space, right? It's not immediately obvious. How does one define addition in the tangent space, right? And, you know, you would like the tangent space to be a vector space of dimension equal to the dimension of the manifold. That is not clear either. So it's not hard to show, but well, you have to think about it a bit to see how you can make this a vector space of dimension n. Okay, but anyway, this is not the definition we're going to take. We're going to take what's really a more algebraic definition. Of the tangent space. Yeah. So any questions about this geometric definition? This is something which maybe you probably would not have seen, I think. So that's why I'm just asking. Any questions? Okay. All right. So we're going to talk about what's the algebraic definition of the tangent space. So here the idea is that, so I take my manifold and I take a point P. Then the idea is that a tangent vector at P gives me a direction along which to differentiate functions in a neighborhood of P, smooth functions in a neighborhood of P. Okay, so the idea is this gives a way to differentiate smooth functions near P. So let me give you an example. So suppose you just take Rn itself. Okay, and I take a point P in Rn. and I take a vector V in Rn, which I'm thinking of as a vector based at P. Okay. Now, if I take, say, F is a C infinity, if I look at F, well, so this gives me the following. This V will give me a map, say nabla sub V, which is the directional derivative in the direction of V. Okay. So this gives me a map from the set of F, which is C infinity in a neighborhood of P to R. F maps to nabla V F of P, right? The directional derivative. Is this clear? So this map will be a linear map, right? This will be a linear map. Well, linear, the thing is, the first thing actually is what is the correct domain of this map, nabla V? Well, I mean, I'm looking at functions which are C infinity in a neighborhood of P, right? But if I have two functions which are, say, equal near P, then their directional derivatives at P will be equal, right?
Right.
So what we should do is look at smooth functions in a neighborhood of P, but we should look at them modulo an equivalence, where we say that F is equivalent to G if F is equal to G in a neighborhood of P, right?
Right.
So that should be the actual domain of our this linear map nabla V. Okay. So this leads to what's called the space of germs of smooth functions near P. All right. So so let me define this for a manifold. So first of all, if for a manifold, if let me first of all define if U is an open subset of a manifold M, then C infinity U is the ring of smooth functions on U. Okay, so F from U to R such that F is C infinity. So this is a ring because the sum and product of smooth functions is easily seen to be smooth. And not just a ring, you can also, it's a vector space also, right? Over R. And the scalar multiplication is, it commutes with the ring multiplication. So actually, this is what's called an R-algebra, right?
Yes.
A commutative R-algebra. Okay. So now, what is the space of germs of smooth functions near P? So this is defined to be, so I'm going to call it C infinity M comma P. So this is defined to be so the set of functions F in C infinity U, where U is an open neighborhood of P. So I look at the set of all functions which are defined in some neighborhood of P. So this neighborhood depends on F, all right? It's not a fixed neighborhood. I can take arbitrarily small neighborhoods of P, and then I quotient by the equivalence that F in C infinity U is equivalent to G in C infinity V, where UV are neighborhoods of P, if there exists a neighborhood W of P such that, so W is contained inside U intersect V, and F restricted to W is equal to G restricted to W. Yeah. Right? So this will give what's called the space of germs of smooth functions near P. So it's easy to see that the addition and multiplication and scalar multiplication of smooth functions, these are compatible with the equivalence relation. So they pass to the quotient. So this also becomes an R-algebra. Okay, this germs of smooth functions near P. It's a ring. It's an R-algebra. Okay. So this would be, in our example, with M equal to Rn, this would be the natural domain of definition for this map nabla V, right? So here really I should take, instead of this set, I should take as domain of nabla V the ring of germs C infinity Rn comma P. Okay, then this map becomes, this is a vector space now, this map becomes a linear map, right? Right, this directional derivative is linear in F, okay, and but that doesn't tell us much. Okay, it's a linear map, but what is the, algebraically, what is the property which captures the fact that this is a derivative? So what is the algebraic way of capturing differentiation?
Leibniz rule.
Leibniz, exactly, right? So the point is, this satisfies the Leibniz rule. So nabla V of F times G at P is nabla V F at P into GP plus FP nabla V G at P. Yeah. So this is a linear map which satisfies the Leibniz rule at P. And it turns out that this purely algebraic property, linearity plus the Leibniz rule at P, this is enough to characterize these maps nabla V. In other words, if I have a linear map from C infinity Rn P to R, which satisfies the Leibniz rule at P, then it must be of the form nabla V for some vector, for some unique vector V in Rn. Okay, so this is the basic fact which will allow us to define the tangent space now for a manifold. Okay, so now let me come to the notes. So, all right, so here we have, as I defined just now, the ring of germs of smooth functions of P, C infinity MP, okay? And now we define now the tangent space to M at P in a purely algebraic way, TPM is defined to be the set of maps D from C infinity MP to R such that D is linear and satisfies the Leibniz rule at P. So D of F times G is D of F into G of P plus F of P into D of G for all Fg germs of smooth functions at P. All right. So this is a purely algebraic definition. Okay. But the good thing about this definition is that with this definition, TPM is obviously a vector space, right? Because the sum of two such linear maps satisfying the Leibniz rule will also satisfy the Leibniz rule, right? And also scalar multiples. So with this algebraic definition of the tangent space, it's clear that the tangent space is a vector space, right? There's no need to prove that or anything. The vector space structure is immediate, right? So in fact, what is it? It's a subspace of the dual space of C infinity MP, right? These are elements of the dual which satisfy the Leibniz rule at P. Yes. Now, the rather remarkable fact is that, so, I mean, this ring of germs of smooth functions, this is clearly infinite dimensional, right? That's easy to see. This ring of germs is infinite dimensional. But now, so its dual space, the dual of this will also be infinite dimensional, right? So if I was to look at all linear maps, I would get an infinite dimensional vector space. But the remarkable fact is that this Leibniz rule at P will actually force this subspace of the dual to be finite dimensional. And not just finite dimensional, it will have dimension exactly equal to n, the dimension of the manifold. Okay, so the key point here is the Leibniz rule. This forces finite dimensionality of the tangent space, and also that the dimension actually equals the dimension of the manifold. Okay. So we're going to prove this, but before proving that this tangent space has dimension n, let's look at some elements of the tangent space which we can define naturally. So for example, if I take a chart, say u comma phi near P, so phi has coordinate functions x1 to xn. It's a map from U, a neighborhood of P into Rn. So let me call Q to be the image of P, so phi of P, that's a point in Rn. Now, this chart phi allows me to define elements of the tangent space, which we'll denote by del del xi at P. So this is an element of TPM. So this is supposed to act on germs of smooth functions f. So how does it act on a smooth function f? Well, you look at, so f is defined near P. So if I look at f composed phi inverse, this will be defined near Q, right? So this will become a smooth function in a neighborhood of Q in Rn. So now this is a function in Rn. I can take its usual ith partial derivative del del xi at the point Q. Okay. So this will define for me. It's clear that this partial derivative is linear and it satisfies the Leibniz rule, right? So this will define an element of the tangent space. Is this clear?
Yes.
Okay.
Yes, sir.
So we get these del del xi's given a chart phi equal to x1 to xn. It defines at all points P in the chart elements of tangent space TPM called del del xi. Okay. Now, so these are some natural elements of the tangent space. Also, we have we can define the tangent vector of a smooth curve as an element of the tangent space. So suppose gamma from an interval AB into M is a smooth curve. So this means that phi compose gamma is a smooth curve for any chart phi, then I can define for any t naught in the interval AB, I can define the tangent vector gamma prime t naught. Now this will be an element of the tangent space. Okay, this will be an element of the tangent space at the point gamma of t naught. So how do I define this? Well, gamma prime t naught, this is supposed to act on functions defined near gamma of t naught. So what do? I look at the function f composed gamma of t. So this becomes a function from R to R, and this is a smooth function from R to R, because I can write this as f composed with phi inverse, composed with phi, composed with gamma. Right? I can just put a phi and a phi inverse in between here. So f composed with phi inverse is smooth because f is a smooth function by definition. And phi composed gamma is also smooth because gamma is a smooth curve. So by definition, so this will become a composition of a smooth function with a smooth curve. So this will become a smooth function. Is this clear? Yeah. So f composed gamma is smooth near t naught. I just take ddt of it at t equal to t naught, right? So it's clear that this will also satisfy the Leibniz rule, right? Okay. By the usual Leibniz rule from one variable calculus, right? It's just the derivative of a function from R to R. So, okay. So this defines for me the tangent vector to a smooth curve as an element of the tangent space. Okay. So this is turning out to be a good definition of the tangent space, right? Where we are able to define tangent vectors of curves in the manifold as elements of the tangent space. We can see that the tangent space is a vector space in a natural way. Now what we want to show is the tangent space is finite dimensional of dimension n. In fact, these del xi's should form a basis. Okay. The idea is that these del xi's will form a basis. So first of all, it's easy to see that del x1 to del xn, these are linearly independent, because if I look at the coordinate functions xj's, these are functions in a neighborhood of P, right? These are smooth functions near P. Then it's easy to see from the definition, del xi of xj is just delta ij, right? Okay. So to show linear independence, if I have a linear combination summation alpha I del xi equal to 0, then I apply this linear combination to the function xj, right? So because del xi of xj is equal to delta ij, in this here left hand side only one term will remain, alpha j into 1. So that means that alpha j is 0. So this is true for all j. So therefore this del xi's are linearly independent. Okay. So they're linearly independent. Now we have to show that they span, right? Now we have to show that they span. So here is where the Leibniz rule is really going to be important. So we have to show that any element D in the tangent space is a linear combination of the del xi's. Okay. So first, let's make some general observations about elements of the tangent space. So intuitively, we're thinking of these as ways to differentiate. So they should give the value 0 acting on constant functions, right? So how do we see that? Well, we use the Leibniz rule. If I look at the constant function 1, then I can write 1 as 1 times 1. So therefore, d of 1 will be d of 1 times 1. By the Leibniz rule, this will be d of 1 into 1 plus 1 into d of 1, which is 2 times d of 1. So therefore, d of 1 is 2 times d of 1. Therefore, d of 1 is 0. Okay. So d vanishes on the constant function 1. And if I take any constant function alpha, where alpha is a real number, then by linearity, I can write this as alpha times d of 1, and that is also 0. So therefore, d vanishes on the constants. All right. sorry, 1 second. Okay. So, right. So the elements of the tangent space vanish on the constants. Now, let's look at the following. So on this ring C infinity MP, I have this evaluation homomorphism, a germ of smooth function f maps to its value at P, f of P. So this is a surjective ring homomorphism, right? It's surjective because the constants go to all of the constants in R. And it's clearly a homomorphism. So if I look at the kernel of this, MP, this is the kernel of this evaluation at P, this will be a maximal ideal of this ring C infinity MP, right?
Yes.
So now suppose I take two functions f and g in this maximal ideal MP. So this maximal ideal means the functions which vanish at P, right? Is the kernel means f of P is 0. So this is the ideal of functions which vanish at P. So let me look at d of f times g. So by the Leibniz rule, this is d of f into g of P plus f of P into d of g. But GP is 0 and FP is 0. So this becomes 0. So that means d of any product of two functions which vanish at 0 at P is 0. And the products of functions in MP, these span the ideal MP squared, right? Yeah, elements of the ideal MP squared are of the form summation Fi Gi, right? Where Fi's and Gi's belong to MP. Yes?
Yes.
So that means this any element of the tangent space D, it vanishes on the square of the maximal ideal MP. Now, intuitively, this should also be clear because you see, elements of the ideal MP, if they vanish at P, if I have a smooth function which vanishes at P, then it is of first order near P, right? That means, I mean, whatever, f of P plus H is big O of H, right? And if I look at a product of two such functions, then that will be second order near P, right? It will be big O of H squared. So for a product of two functions, if something is of second order, its derivative should be 0, right? If something is big O of H squared, then its derivative should be 0. So that's the intuition behind this fact that D vanishes on the square of the maximal ideal MP. Because these are second order elements. These are functions which are second order near P. Okay. So we're almost out of time. Let me stop this and we'll start a new session. Okay. Yeah. Okay. Okay. So, all right. So elements of the tangent space vanish on the square of this maximal ideal. The square of the maximal ideal, you think of as functions which are second order near P, right? Which vanish to second order near P. And they vanish, any element of the tangent space vanishes on the constants. Now the idea is, given any smooth function near P, what I want to do is use its second order Taylor approximation near P, right? So it should be what? It should be a constant f of P plus a first order term that would be the derivative. And then there would be a first order term, and then there would be a second order term. So any element of the tangent space D, it would vanish on the constant part and it would vanish on the second order part. So it would only act on the first order part, right? Okay. So the idea is that you can write actually C infinity MP So this is the sort of second order Taylor formula that we want to have. Any smooth function f here will have a constant part, f of p. So that's the constants. Then there will be a part, a first order part, which vanishes. So, well, I can write it like this, certainly. Okay. But I want to further break this down. This MP, so this MP I can write as the direct sum of
MP modulo MP square.
not exactly, no. It would be the direct sum. I goes from 1. So what are the functions which vanish at P? So what are some examples of functions which vanish at P? Those would be the functions xi minus xi of P, right? These vanish at P.
Yes.
Right? Okay. So these are linearly independent. You can see, it's not hard to see, right? And then what remains would be an NP squared. So this is the sort of direct sum decomposition we want. All right. Okay. So the way to do this is essentially a sort of Taylor formula. But we just have to be a bit careful about it. So let me do that now. All right. So, okay, let's do this. So given a function f, which is a smooth function near P, let's look at f tilde, which is f composed phi inverse. Phi is my chart near P. So this is a germ of smooth function near Q, where Q is phi of P. Okay. Now, if I take x, which is a point near Q, I look at f tilde of x, right? So then what I can do is I can consider the straight line from Q to x, and I write f tilde as the integral of its derivative along this straight line, right? I just use the fundamental theorem of calculus. So f tilde of x will be f tilde of q plus the integral from 0 to 1 ddt of f tilde of q plus t x minus q dt. Is this okay? This q plus t x minus q, this is the straight line from q to x, right? And then I'm restricting f tilde to this straight line. I'm differentiating and I'm integrating. So I'll get back f tilde, right? Okay,
Yes.
this is just the fundamental theorem of calculus. Now what I want to do is I use the chain rule in this derivative, right? So the chain rule, this is the sum I goes from 1 to n, del xi of f tilde at the point q plus tx minus q into xi minus qi. Now, I've skipped a step here. The term which I wanted is this term, del xi of f tilde at q plus tx minus q. What I do is I subtract from this del xi of f tilde at q, and I add also del xi of f tilde at q. Okay, so I add and subtract this term. So then what happens? This xi minus qi, these are constants. They don't depend on t. So they come out of the integral. And so then I get a sum like this. So here, well, these don't depend on t. This is just a constant. So what I'll get is f tilde of q plus sum over I. What is del xi of f tilde at q? This is by definition the element of the tangent space del del xi acting on f, right? This is by definition del del xi acting on f into xi minus, there's a typo, this should be qi, xi minus qi, and then plus sum over I have this xi minus qi into this integral. This integral is a function of x, which I will call gi tilde of x. So there's an I missing here. There's another typo, sorry. So I have this expansion of f tilde, and from this I get an expansion for f, right? So f tilde is f composed phi inverse. That means f is f tilde composed with phi. So if I put x equal to phi of y, where y is in the chart u near p, then I get that f of y will be f of p plus sum over I del del xi of f into xi of y minus xi of p, right? Okay, this qi is xi of p, this xi is xi of y, okay? Plus, what is this second, this last term here? It's a sum xi of y minus xi of p, that's this term, into some function gi tilde of phi of y, right? Where gi tilde is this function of x. Now notice this function of x, this vanishes when x is equal to q, right? If x is equal to q, this term becomes 0. I just get del f tilde del xi of q minus del f tilde del xi of q. This integral is 0 when x is equal to q. So therefore, this gi tilde of phi of y, this will vanish at p. And also this xi y minus xi p, this also vanishes at p. So therefore, this is an element of MP, and this is also an element of MP. So we've got the decomposition that we wanted, right? We have a constant plus a sum of these coordinate functions xi minus xi of p plus an element of MP squared, right? Is this clear?
Yes, sir.
Yes.
So now when I apply, if I take any element d of the tangent space, if I apply it to this f, then d of f will be what? It's going to vanish on the constant, and it's going to vanish on this element of MP squared. So it's just going to act here, right? And when it acts here, these del f del xi, these are constants, and d is linear, so these will come out, and then it's going to act on xi minus xi of p, but xi of p is a constant, so d of that will be 0. So finally, what will you get? D of f will be the sum over I, d of just xi into del del xi of f, right? Is this clear?
Yes.
So what does that mean? That means that for every f, d acting on f is given by some constants, this d of xi, into del del xi is acting on f, right? In other words, d is therefore equal to this linear combination of the del del xi's, sum over I, d of xi into del del xi at p. Is this clear?
Yes.
Okay. So therefore, this tells me that the del del xi span, right? And we already saw they're linearly independent. Therefore, they form a basis, and the tangent space is of dimension n. Okay. And the del del xi's are a basis of the tangent space. Okay. And not only a basis, but we have an explicit formula for any element of the tangent space. We have an explicit formula for how to write it as a linear combination of the del del xi's, right? You just let d act on the xi's, and those give you the coefficients of the linear combination. Okay. So is this all right? Yeah.
Yes, sir.
So now let's move on to so just briefly, I just want to talk about what's called the tangent bundle of a manifold. So, I mean, first, let me just give you a picture so that it's not too abstract. So now that we've got the tangent spaces, so the tangent bundle so abstractly is just the disjoint union of the tangent spaces. But what I want to say is this is also a manifold of dimension 2n, 2 times the dimension of the manifold n, because intuitively you have n dimensions for the base point P, and for each point P you have n dimensions for the vector in the tangent space TPM. So there should be n plus n dimensions. But let me just give you an example, a standard example, so you have some picture in mind. So if I take, say, S2 in R3, so then what will the tangent space be, or the tangent bundle rather? So it would naturally be pairs P together with a vector in the tangent space. But what is a vector in the tangent space here? The tangent plane to the sphere is just the orthogonal complement of the radius vector, right? Yes, tangent to the sphere is orthogonal to the radius vector. So this V's in the tangent space would just be the orthogonal complement of P, right? So in this case, the tangent bundle of S2 would be the set of pairs P comma V. So this would be a subset of, so this is in R3 and V is in R3. So this would be in R3 cross R3. Where P belongs to S2, so norm P is 1. And V is perpendicular to P. Okay. Does this make sense?
Yes.
So this would be the tangent bundle. So the union of these tangent planes, you see. Yeah, but you put it inside R3 cross R3 so that all of these tangent spaces become disjoint, right? These are all disjoint because they've got a different first coordinate. Okay. And this, it's easy to see this as dimension 4 because you're sitting inside R6 and you have 2 constraints, right? Norm P equal to 1 and inner product PV equal to 0. So each constraint cuts the dimension by 1. So the dimension will be 6 minus 2, that's equal to 4, right? Is that clear?
Yes.
Okay, so this has the expected dimension. Sorry, 6 minus 2 equal to 4. 6 minus 2 equal to 4. Okay. All right. So now, in general, what we want to say is that the tangent bundle will be a manifold of dimension 2n. Okay. So first of all, we have this projection map pi from the tangent bundle to the manifold, which, so I think of, I write elements of the tangent bundle as pairs a base point P together with a vector V, which is in the tangent space TPM. Okay. So we have this projection P comma V maps to P, right? Okay. You map each tangent vector to its foot, to its base point. Now, suppose I have a chart on M, okay, that will naturally give me a chart on the collection of tangent spaces lying above U. So U is an open subset of N. So I look at all tangent vectors whose base point lies in U. So that means the set pi inverse U. So this is an open subset of Tm. Okay, well, I haven't given a topology actually. So rather, the topology will come from these charts actually. So, okay, so let me look at the set pi inverse U. So any point here, I can write in the form P comma. So I know that once I have a chart phi, then it gives me a basis of the tangent space at each point P. The basis is del del xi at P. So any vector I can write in the form summation ai del del xi at P. Okay. So what I do is I map this P comma this V, I map it into phi of U cross Rn, which is an open subset of, well, this will be a subset of R2n. P goes to phi of P, and this summation ai del del xi at P, this goes to just the vector a1 to an in Rn. All right. So actually, this will map to all of phi of U cross Rn, right? Because as you range over the tangent space here, the a1 to an will range over all of Rn, right? Okay. So, so this is an open subset of R2n, okay? And this map is a bijection, right? This map is a bijection, yeah? So I want to use these bijections to define a topology on Tm, right? So the topology will be, if I take a point in pi inverse U, I just have to say what are neighborhoods of it, right? So I'll say a set is a neighborhood of it if the image of it under phi is a neighborhood in R2n, right? Does that make sense? Yeah. Okay. So if I take an element of the tangent bundle, say P comma V, what is a neighborhood of P comma V? It's a set whose image under phi is a neighborhood of the image in Rn, right? Is an open set in Rn, in R2n, sorry, in R2n. Okay. Right. So the idea is that these phis will give us charts. This capital phi will give us charts on the tangent bundle. So I have to check that the change of charts is smooth, right? So this chart capital phi came from a chart little phi on M. Now I want to see if I choose a different chart little psi on M on the same open set U. So then I will get a different chart on pi inverse U. So let's look at that. So psi I write as say y1 to yn. It has coordinates y1 to yn. So then psi will give me a basis of the tangent space del del yj, right? But now by this formula that we have here, for any element of the tangent space, d equal to sum over I d of xi del del xi, I can write therefore del del yj as sum over I del del yj of xi del del xi, right? Now the xi's are smooth functions. So del del yj of xi, this will be some smooth function aij of p, right? Okay. So therefore del del yj is equal to a sum over I aij into del del xi. Okay. So this is a change of basis formula, right? where the coefficients are smooth. Is this clear?
Yes.
So now, if I look at the chart induced by little psi, let me call that capital psi. So what does capital psi do? So capital psi of a tangent vector of a point in Tm, p comma. So when I write it in terms of the basis del del yj, so I write it as sum over j, bj del del yj. So this maps to psi of p comma b1 to bn. Okay, so I'm writing my vector v as summation bj del del yj. But I can also, using this change of basis formula, I can write it in terms of the basis del del xi, right? So del del yj I substitute as sum over I aij del del xi, and then I interchange the order of summation. So this becomes sum over I, and then you have sum over j aij bj into del del xi, right? So that means that under the chart capital phi, my coefficients of del del xi will be basically the summation aij bj. In other words, if I take the matrix whose entries are aij, then it's just the matrix A into the column vector B, right? So therefore, if psi maps to psi of p comma b, then capital phi will map p comma v to phi of p comma a of p into b, right? Where A is this matrix aij. Is this clear?
Yes, sir.
Okay, the same vector v I'm writing in two ways. In terms of del del yj's, the coefficients are bj, or I'm writing in terms of del del xi's, the coefficients are summation aij bj, right? So these bj's will map under capital psi to the column vector b, and this summation aij bj, this will map to the column vector a into b, capital A into b, right? So, so therefore, if I look at the change of charts now, phi composed with psi inverse of a point x comma b, what will it be? It will be phi composed psi inverse of x, comma a of psi inverse x into b. Okay. Right? X is psi of p. So here this a of p, p will become psi inverse of x. Okay. And so psi is smooth, a is a smooth matrix valued function. So this will be smooth in the pair x comma b. Okay. This phi composed psi inverse this is the change of charts for m. So this is smooth in x. All right. So the whole thing is smooth as a map from R2n to R2n. Is this clear?
Yes, sir.
Yes, sir.
So this gives us, therefore, we get charts on Tm, right? So therefore, Tm becomes a smooth manifold of dimension 2n. Okay. All right. So the tangent bundle is a smooth manifold of dimension 2n. So now we can say what is a vector field. Okay. So again, the picture is very simple. A vector field means I have my manifold, and at each point I choose a tangent vector in the tangent space at that point. Okay, so I could have a vector field which looks something like this. Or I could have a vector field which looks something like this. And the idea is just like vector fields in Rn, they give you integral curves. They give you a differential equation, an ordinary differential equation. And solving that ordinary differential equation, you get integral curves of the vector field. Similarly, the idea is that a vector field on a manifold will give you integral curves, which will be smooth curves in the manifold, right? So in this example, for this vector field, the integral curves will be longitudes. And for this vector field, the integral curves will be latitudes. Of course, notice one small point here, which is, which is really a topological point, that on this two-sphere, this vector field, if you want it to be continuous, it has to vanish at the poles here, at the north and south pole. This vector field has to vanish here if you want it to be continuous. Similarly, this one also has to vanish at the north and south poles. Can you see that, right? Because if I look at this in a chart, what this is going to look like near the north pole is something like a radial vector field, right? Okay, so the only way for this to be continuous is if the length of these vectors goes to 0 at n, right? Is that clear?
Yes.
Yeah?
Yes. Yes.
And for this one, if I look in the chart, then the vector field you'll see is like a, it's this vector field rotated by 90 degrees. Okay. And so this again, for this to be continuous, the length of these tangent vectors has to go to 0, okay, at the north pole. So this will have to have zeros at the north and south pole. And I'm sure you all know the Harry-Ball theorem that any continuous vector field on the two-sphere has to have at least 1 0, right? So you can see it in these pictures. These have to have at least 1 0. Okay, so let's come to the abstract setup. So, all right, so what is a vector field on a manifold? So on an open subset of a manifold, say. So it's a smooth map from the manifold to its tangent bundle. So both of these are manifolds, so it makes sense to talk of a smooth map, right? Such that x of p belongs to TPM for all p in U. Right? So that's just what I'm saying. At each point p, you choose a vector in that tangent space, TPM. All right. So locally, I know that I can write any tangent vector in terms of the basis del del xi. So that means my vector field locally I can write as a summation ai del del xi, where the ai's are functions, the coefficients are functions of p in the manifold. And these, to say that the vector field is a smooth map here is the same thing as saying that these functions ai are smooth functions, right? Because what is the smooth structure on the tangent bundle? It was coming from, this was a chart, right? Phi, capital Phi. So here, I mean, capital Phi composed with my vector field will just give me this A1 to AN, right? So this A1 to AN should be smooth functions. Is this clear?
Yes.
Right, I mean, I have x is going from the manifold, so a subset of the manifold to this subset of the tangent bundle pi inverse u in Tn. And here I have my chart capital phi. Right? And this is mapping into Rn cross Rn. Okay. So what does this map look like? Its P goes to, so I have to take I have to choose a tangent vector at P. So the base point will be P, and then I'll have some summation AI of P del xi at P. And then this under my chart goes to what? This goes to phi of P, comma, A1 of P, AN of P, right? Yes?
Yes.
Sir.
Yes.
So this composition, so to say that X is smooth means that when I compose with a chart, this is smooth. So that's the same thing as saying that this A1 to AN is smooth, right? Okay.
Yes.
That's okay. All right. So okay, so a smooth vector field just means you choose a tangent vector at each point such that the coefficients with respect to the basis del xi locally, these are smooth functions. Okay. So let's introduce a notation. Chi of u is the space of smooth vector fields on U. Okay. So note that you can add vector fields pointwise, right? So they form a vector space. You can add and take scalar multiples of vector fields pointwise. So the space of smooth vector fields on U will be a vector space. Now we want to come to what are integral curves of a vector field. So gamma, a smooth curve in N is called an integral curve of X if it satisfies this following ODE. So gamma prime T is equal to X of gamma T. Now, what is the meaning of this ODE? Remember, for any smooth curve, we defined gamma prime T as an element of the tangent space at gamma T, and also X at the point gamma T. By definition, this is an element of the tangent space at gamma T, right? So this equation makes sense. Both sides are elements of the tangent space at gamma T. Okay. So this is the ODE that we want a integral curve of X to satisfy. Okay. Now, what we can do is, once we take local coordinates near a point P, this ODE will turn out to become just an ODE in Rn actually. Okay. So let's see how that happens. So suppose phi equal to x1 to xn is a chart near gamma of T naught, which is a point in U. Okay. So let me look at the curve gamma tilde of T. All right. So that means phi composed with gamma. So this is a curve in Rn now. So this, let me say this has coordinates x1 of T up to xn of T. Okay. This is a curve in Rn. All right. So let's first work out what is gamma prime T in terms of the basis del xi, right? What is gamma prime T in terms of the basis del xi? So if I take any function f, which is a germ at the point, a germ of smooth function near gamma of T, then by definition, what is gamma prime T acting on f? It is ddt of f of gamma T. Now this I write as ddt of f composed phi inverse composed with phi composed gamma. Okay. So f composed phi inverse, let me call this f tilde, and phi composed gamma, this is gamma tilde. So now f tilde is a function from Rn to R, and gamma tilde is a smooth curve in Rn. So by the chain rule, this will be sum over I del f tilde del xi at the point gamma tilde of T into xi prime of t, because gamma tilde has coordinates x1t to xnt, right? So this del f tilde del xi at gamma tilde of t, this by definition, this is nothing but del xi at gamma t applied to f, right? So this sum I can write as this linear combination of the del xi's, summation xi prime t del xi at gamma t, the whole thing applied to f. All right. Is this clear?
Yes, sir.
Yes.
Okay. So therefore, I can write gamma prime t is equal to sum over I xi prime t del xi. Okay, so this is the expression of gamma prime in terms of the basis del xi. Okay, the coefficients are just xi prime t, where in the chart phi, gamma has coordinates x1t to xnt. Okay. Now, what does my differential equation, my ODE become then? This gamma prime t equal to x of gamma t. This means therefore that summation xi prime t del xi is equal to summation ai of gamma t del xi. So I'm writing x as summation ai del xi, where the ai's are smooth functions on the chart U. Okay. So x of gamma t will be summation ai of gamma t del xi. Okay. Now del xi's are a basis. So this equation means that the coefficients of del xi's have to be equal, right, for all I, right? And if I want to write this as an ODE in Rn, what I do is I write this ai of gamma t as, again, ai tilde of gamma tilde, where ai tilde is ai composed with phi inverse, and gamma tilde is phi composed with gamma. Okay. So then the ai tildes are now smooth functions in Rn, right? And gamma tilde is a smooth curve in Rn. And this xi primes are the components of the derivative of gamma tilde. So when I equate coefficients here, what I'll get is xi prime is equal to ai tilde of gamma tilde. And xi primes are the coefficients of gamma tilde prime. So this equation therefore is equivalent to ddt of gamma tilde equal to x tilde of gamma tilde t, where x tilde is the vector field in Rn with okay. Okay. Okay, so sorry, I got cut off in the middle. All right. So right. So this ODE gamma prime t equal to x of gamma t. We see that we write each side in terms of the basis del xi, and then this becomes an ODE in Rn, right? ddt of gamma tilde is equal to x tilde of gamma tilde t, where x tilde has coefficients a1 tilde to an tilde, where each ai tilde is ai composed with phi inverse. So these are smooth functions in Rn, right? Is this clear? Yeah.
Yes.
Right? Okay. So that means an integral curve in the manifold is basically a curve such that when I look at it in a chart, this gamma tilde is nothing but phi composed with gamma. This is a curve in Rn. So the curve in Rn satisfies an ODE in Rn with smooth coefficients. Okay. So therefore, for Rn, we know that we have the local existence uniqueness theorem for ODEs in Rn. Therefore, we get local existence and uniqueness of integral curves for a vector field on a manifold, right? Okay. So that means that for any point P in the manifold, there will be a unique integral curve defined on an interval around 0, such that gamma of 0 is equal to P, right? So for any point, there will be a unique integral curve passing through that point, okay, defined in some interval around 0. Is that clear?
Yes, sir.
Yes. Yes.
Okay. So that just follows from the theorem for ODEs in Rn. Now, well, the theorem in Rn will just give you local integral curves. So then you may want to ask, what about global integral curves? Do I have integral curves which are defined for all time? Right? Now, even in Rn, actually, this is an issue, right? We know that there are vector fields in Rn whose integral curves are not defined for all time, right? So, I mean, basically, solutions can blow up in finite time. They can go to infinity in finite time, so they may not be defined for all time. But what we can always do is construct what's called maximal integral curves. So suppose we have an integral curve gamma on an interval I, an open interval I mapping into M. So we'll say that this is maximal if there does not exist an integral curve gamma tilde on an open interval J such that J strictly contains I and gamma tilde restricted to I is equal to gamma. So that means we cannot extend it to a strictly larger interval as an integral curve. All right. So then we'll say an integral curve is maximal. And then, like you show for vector fields in Rn, the same argument will tell you, it's just an abstract nonsense argument, really. Will tell you that for any point P in the manifold, there is a unique maximal integral curve, gamma P, defined on a unique maximal interval IP, which contains 0, okay, such that gamma P of 0 is equal to P. All right. So for any point, there is a unique maximal integral curve starting at that point. Okay, defined on a unique maximal interval IP. And what we need for later is what's called the local flow of a vector field. So this is just like in Rn, for vector fields in Rn. The local flow, I mean, it's in terms of pictures, it's just you have your vector field on your manifold, and the local flow is if I take a time t in R. Let me suppose, just for simplicity, that the maximal integral curves are defined for all time. Okay. So then the local flow is basically I take the integral curve passing through P and I flow along it for time t. So this point would be gamma P of t. And this I define to be phi t of P. So phi t therefore will be this map. Okay, so phi t will be the map. M to M. P maps to gamma P of t. Okay. Now, this is if the maximal integral curves are defined for all time. So in general, they won't be defined for all time. But what will happen in general is, given any point P, there will be a neighborhood of P. So in general, given P, there exists a neighborhood of P and there exists epsilon positive such that for all points in this neighborhood, the integral curves are defined for time at least epsilon. Okay. So let's say for all Q in the neighborhood U, the interval minus epsilon to epsilon is contained inside the maximal interval I sub Q. Okay, this is the domain of the maximal integral curve starting from Q. Okay, so this is a subset of R. Then we can define the local flow, which will be a family of maps phi t from U subset of M to M mod t less than epsilon Q maps to gamma Q of t. Okay, is the definition clear?
Yes.
Yes.
So, right. So the local flow given a point P, we'll get some epsilon so that the maps phi t are defined in a neighborhood of P for all t less than epsilon. Okay. Okay. So the main property that we need is that these maps phi t, they form a one parameter group. So phi t composed with phi s is phi s plus t. Okay. Now, the only thing you have to be a bit careful with this statement, if the integral curves are not defined for all time, if they're just locally defined, then, well, you just have to say, I mean, this equation holds wherever it makes sense. All right. So I'm not going to write that out, but you understand what I mean, right?
Yes.
Okay, for ST small and in a neighborhood of P, this will be true. Okay, for ST small, let's say less than epsilon by 2, or okay, well, they have to be appropriately small, actually. So that, I mean, these land, I mean, phi t of P should also stay inside U and so on. Oh, so I'm not writing it. It's a bit complicated to write. But for ST small and close to, this holds close to P. Okay. But what we do get is that these are locally their diffeomorphisms. So, you know, phi minus t, therefore, will be the inverse of phi t. This is something we need. Okay. And of course, phi 0 by definition is identity. Okay. And the integral curve through P is by definition just T maps to phi T of P. Okay. And so the vector field X at P, I can get by differentiating the flow. This is by definition, it's the derivative of the integral curve at time 0. So this is ddt at t equal to 0 of phi t of P. Okay. All right. Okay. Fine. So, right. Yeah. So one small definition here that a vector field is complete if all of the integral curves are defined for all time. So, for example, if I take a compact manifold without boundary, then any vector field on n is complete. So, for example, in this example of the two-sphere S2, these vector fields are complete. Okay. Any vector field on S2 will be complete. So, in general, on any compact manifold, any vector field will be complete. Okay. All right. So now I need something important for us, which is to define the Lie bracket of vector fields. So again, there are broadly two ways to do this. There's a geometric way and there's an algebraic way. So let me first do the algebraic way. Then we'll come to the geometric way of doing this. So the algebraic way is, well, it's very algebraic. It involves what's called the derivations of the ring C infinity M. Okay. So this is a purely algebraic construction. So if I have an, this is a purely algebraic construction. So if A is an R algebra, then we can define der of A. This is going to be the space of what's called derivations of A. So this is defined to be the space of linear maps D from A to A. Such that D, it satisfies the Leibniz rule. D of F times G is D of F into G plus F into DG for all FG in A. Okay. So what's an example? Example, you take A to be, let's say, the polynomial ring in one variable. Okay. And I can take D to be the map from A to A, which is just ddx. So a polynomial P maps to dp dx. All right. Or yeah, this would work. So this would be a derivation. Okay. So again, since we're doing things purely algebraically, here's another purely algebraic fact. So this is just algebra. So if for D1 on this space, this dere, well, this is clearly a vector space, but this has an additional operation called the Lie bracket. So the Lie bracket on dere, so Lie bracket on the space of derivations. This is purely algebraic. So notice if D1 and D2 are derivations of the algebra A, so they're linear maps from A to A. Okay, so I can compose them. So I can look at D1 composed with D2, and I can also look at d2 composed with d1. Okay. Now, in general, the composition of two derivations will not be a derivation. You can just see that in this example, right? If I look at d composed with d, this becomes d squared dx squared. So this does not satisfy the Leibniz rule, right? This does not satisfy the Leibniz rule. It's a second order derivatives. But what happens is, if I take the composition of two derivations, d1, d2 and d2, d1, the difference does satisfy the Leibniz rule. So this actually will be a derivation. Okay. So this is defined to be the bracket of the two derivations, d1, d2. Okay. All right.
Yes.
Okay. So this is just you just check that this satisfies the Leibniz rule. You do the computation and you'll find that certain terms cancel, and this will satisfy the Leibniz rule. So this is just algebra. There's no smooth functions, no differentiation, nothing, just algebra. Okay. You have any A algebra or any R algebra A, and then the space of its derivations will also be it will have this Lie bracket operation. Okay. It will have this Lie bracket operation. Okay. So now the point is that if I look at A equal to C infinity M, okay, then any X, a vector field, a smooth vector field on M, this gives a derivation of C infinity M. So let me call it D sub X. Okay. So F maps to, so let me just call it XF. Okay. So where XF at a point P, this is going to be a function. This is supposed to be an element of C infinity M. So what is its value at P? XF at P is defined to be, so F is a smooth function on M. So it defines a germ at P, right? It defines a germ of smooth function at P. And X at the point P is a tangent vector at P. So X at P acts on smooth functions near P. So I let X at P act on F. All right. Is this clear?
Yes.
Yes, sir.
Okay. Now, because X at P satisfies the Leibniz rule at P, that means that this XF will satisfy the Leibniz rule, right? So X of FG will be XFG plus FXG. Okay. And the point is that actually this map, so then I get a map from chi M to the space of derivations of C infinity M. X goes to the derivation D sub X, right? Yes. What's easy to show, what's not too hard to show, this map is an isomorphism. This map is an isomorphism. Okay. So isomorphism of vector spaces. Okay. All right. So, I mean, it's in the notes, but I don't want to spend too much time on this. It's not very difficult. I mean, you have to define a map in the opposite direction, right? If I have a vector field, if I have a derivation D, then I have to define a vector field X sub D, right? Okay. I have to define to show it's an isomorphism, I define an inverse of this map. So that's done in the notes. I'll just briefly say how you define this. So suppose I have a derivation, I have to define a vector field, right? So this X sub T, given given D, a derivation, you want to define a vector field X equal to X sub D in chi M as follows. So we have to define at each point P what is XP, right? So XP is supposed to be an element of the tangent space. So this acts on smooth functions near P. So I have to say what is XP of a germ F, right? Yeah. Now,
Yes.
well, I define this to be the following. So F is just a germ of smooth function near P. But I can take a bump function. I can multiply F by a bump function near P and then extend it to a smooth function on all of M, right? Now, once I extend it to a smooth function on all of M, then my derivation D can act on F, right? So I extend F to a smooth function F tilde on M, okay? And then I let D act on F tilde. So this gives me again a smooth function on M, right? And then I evaluate this at P. Okay. Right. So this is for F. This is a germ at P. And here F tilde is a global function such that, well, it's equal to F in a neighborhood of P. That means the germ of F tilde is equal to F. Okay. Is this clear?
Yes.
Yes.
So then you have to show this is well defined and so on, right? Independent of the choice of extension. So that's done in the notes. I won't spend time on this. All right. It's not very hard. Okay. Is it all right? So I'll skip this. I'll just
Yes.
skip this.
Yes. Yes.
Okay. So yeah, so this gives you the map in the opposite direction, and then you can check these two are inverses of each other. All right. So yeah. Okay. So any vector field gives you a derivation of C infinity M, and conversely, any derivation of C infinity M gives you a vector field. And these two maps are inverses of each other. So now what I can do is in this isomorphism, on the right-hand side here, right, I have the bracket operation, the Lie bracket operation. So I can just use this isomorphism to transfer it back to the space of vector fields, right? So given now, given X, Y in chi M, you define bracket XY in chi M. So to define this vector field, it's enough to say what its action on smooth functions is, right? So by putting, so we define bracket xy acting on a smooth function f in C infinity m. This is defined to be the bracket of the derivations, right? So this is x, y acting on f minus yx acting on f. Is this clear?
Yes, sir.
Yes.
So this might all seem a bit abstract. If you want to see it concretely, what is happening? So in local coordinates, f is summation ai del del xi, right? And y is summation, say, bj del del yj, sorry, del del xj. This x is what? It's nothing but a first order differential operator, right? A first order linear differential operator, right? So a vector field is the same as a first order linear differential operator, right?
Yes.
Right? A vector field is nothing but a first order linear differential operator. And so the product of two vector fields, x, y, right? So this acting on f, this will be a second order differential operator, right? Yeah, xy will be a second.
Yes.
So what will this be? So it will be summation ai del del xi of sum over j bj del del xj. This applied to f. So let me apply it to f here. Okay. So now what will happen? Let me look at the highest order term, right? So in the highest order term, that will be of degree 2, right? In the degree 2 term, basically I won't differentiate the bj. I'll just differentiate the del f del xj, right? So the higher order term, the highest order term will be sum over ij ai bj del squared f del xi del xj, right? So plus
Yes.
lower order. This is the highest order term, right? Is this clear? Yeah.
Yes.
Now similarly, what will yxf be? So I do the same thing. I write this formula. This will then become a sum over ij, well, bj ai del squared f del xj del xi, right? Plus lower order. Now what happens when I take the difference? You see these two, the first order, the highest order terms are equal, right? Because of equality of mixed partial derivatives, this highest order terms are equal. These highest order terms are equal. So when I take the difference, the second degree terms cancel. So what remains is a first order differential operator, which is a vector field. Is this clear now?
Yes.
Yes, sir.
Yeah, maybe this makes it less abstract, right? And using this, you can calculate explicitly what is the bracket in local coordinates, right? Yeah, you can explicitly calculate what is the bracket in local coordinates.
Yes,
Yeah?
yes.
You have the formula for x, you have the formula for yxf, you subtract and you'll get the formula for the bracket acting on it. Okay. All right. So, okay. So any questions so far? Okay, so I'll just say that, I mean, you can take products of vector fields, right? So if I take a product x1 to xn, this will be a nth order differential operator, All right. And yeah, so I mean, this is sort of, you can actually take the, well, I don't know how to, what the notation should be. You can take the universal enveloping algebra of the, well, the vector, the space of vector fields becomes an infinite dimensional Lie algebra with its Lie bracket. And you can take its universal enveloping algebra. This will be the algebra of all differential operators.
Yes.
This will be the algebra of all differential operators on of all orders on M. Okay. Does this make sense? Yeah.
Yes, sir.
Yes, sir.
I think that's a correct statement. I have to check, but I'm just saying this, but I think that's a correct statement. So this will be the algebra of, I think it's called the Weil algebra. I think this is called the Weil. So this is the algebra of all differential operators. Okay. All right. So we don't have much time, just 5 minutes. I don't know if I should do anything more. Let me just look at the notes for a second. Right, so we have the brackets. Okay, I think, yeah, it's no point starting anything new now. Yeah, it's just 5 minutes left. So yeah, if you want to discuss anything, any questions, we can just talk a bit if you want. I don't know if you have anything to discuss. Yeah. I mean, this is all very classical, approach to manifolds. The one thing I will say from a personal viewpoint is this is all very algebraic, right? It's a very algebraic approach to tangent spaces, vector fields, Lie bracket, even derivatives of functions and so on. It's a very algebraic approach. It works well for manifolds, but personally, well, you end up looking at spaces which are not manifolds, which are not smooth, just metric spaces. And then you would like more geometric ways of defining things. For example, tangent spaces, for example, tangent spaces. So maybe to finish, I'll just wave my hands a bit and talk about, well, not talk, I mean, I'll just say that, how do I mean, in geometry, people do define tangent spaces for metric spaces, which are not manifolds. So what one does is, if you have a metric space, say XD is a metric space, then the idea is basically, let's look at the smooth case first, and then that will motivate the general definition. Yeah. So suppose I'm looking at a piece of a manifold. So it's a curved space, right? So let's say the two spheres sitting inside R3, standard example. So what happens if I start to blow up? So I want to define the tangent space at a point P. So the idea is you can, you can blow up small neighborhoods of P into larger neighborhoods. Okay. So blow this up. Now, as I keep blowing up, what will happen is eventually these will become flat, right? In the limit, as I keep blowing up a smaller and smaller neighborhoods of P, I keep blowing up to, let's say, unit diameter. This will, in the limit, I'll get something flat, right? Now, what does it mean to blow up? When I say blow up, what I mean is So I'm looking at, let's say, X with my base point, P, and I'm looking at the metric D, right? So blow up means I look at X with the same base point P, but now I take N times the metric D, right? So my distances near P will become very large. I mean, will have become multiplied by N. All right. So I'm sort of blowing up near P. And then the idea of Gromov is to take what's called a Gromov-Hausdorff limit of this. And this will be the tangent space.
Kinshuk, you may not have time now.
I know. So I'm not saying anymore. I just wanted to give this little idea.
Yeah.
This is Gromov's idea. I think this is Gromov's idea. So, that's all. I know we're less than a minute. So I think.
Yeah.
So
So you can
maybe let's
elaborate
say
on this in the next class.
Gromov-Hausdorff limit. Yeah.
Yeah. I know I won't say more about this, but I just wanted to give a little idea. Yeah. It's a nice idea of Gromov. So that's okay. So I'll see you next week, Tuesday then. Yeah. Okay.